This looks like one oven window. It is not. Depending on the model, that dark rectangle can hide 2, 3, or 4 separate panes. And those layers are not just backups. Together, they turn an opening in an insulated oven wall into a transparent thermal system. The familiar answer is that trapped air insulates. That can be part of the story. But heat also conducts through solids and edges. Gas still transfers energy across a gap, radiation crosses it too, and some documented doors deliberately move room air. So what is the complete assembly changing? Start with the design problem. The opaque walls around an oven can hide conventional insulation. The door must still let you look into the cavity. It needs a clear path for visible light while reducing heat transfer toward the room-facing surface. That is why this is not merely a thicker piece of glass. Heat has 3 routes through this picture. It conducts through solid glass, frames, and edge supports. Gas between panes can conduct and circulate. And warmer surfaces exchange thermal radiation with cooler surfaces across the same space. A real door has to manage all 3 at once. Now add a second pane. The sheet adds another solid layer and, crucially, creates another boundary and controlled space. That separated gap interrupts a continuous solid path, yet it is not empty, and the gas inside it can still transfer energy and circulate as temperatures separate. Radiation is the route the air explanation misses. It does not need the gas to carry it from one pane to the next. Some doors, therefore, add a heat-reflective coating to one or more surfaces. That changes the radiation branch. It does not block every kind of heat, and its presence and position vary by model. Here is the topology in one deliberately simplified model. Its one-pane heat flow index starts at 100. Add 2 clear gaps, and the index becomes 35. Change one radiation branch to an illustrative low emissivity case, and it becomes 30. Those are normalized model outputs, not degrees, measured efficiency, or data from any oven. The numbers are not the lesson. The changing network is. Each gap adds a place where gas transfer and radiation operate in parallel. Each additional stage can increase the resistance of the complete path. And a radiation control surface affects only the branch it was designed to affect. But now trapped air breaks down. One peer-reviewed study modeled a particular four-pane pyrolytic door with a closed gap, heat-reflective inner panes, and a cooling circuit elsewhere in the assembly. The same door could use still gas in one region and moving air in another. Why move air at all? In an open channel, warmer air can rise and draw cooler room air into the door. Other systems can use a fan-assisted cooling path. That airflow carries energy away from selected parts of the assembly. It may help manage exterior temperatures, but it also means the door is not simply sealing every joule inside. That is why pane count alone cannot rank an oven door. Current documentation includes a 2-pane Bosch example with a cooling fan, a 3-pane Bosch example with a cooling fan, a 3-pane SMEG example with thermo-reflective panes and cooling, and a 4-pane IMI-ELU example with coatings and an open airflow system. Even 2 doors with the same number of panes can behave differently. Gap spacing, coating, pane orientation, seals, edge supports, frames, airflow, cavity mode, and room conditions all change the path. A fan listed on a product sheet does not prove that it blows through a particular glass gap. More stages also bring trade-offs: more material, mass, thickness, cost, reflections, and model-specific cleaning requirements. Thermal bridges around edges can bypass the neat center of glass picture. And moving cooling air can lower temperature in one region while carrying useful heat toward the room. The desired consequence is not a door that is universally cold or safe to touch. accessible exterior temperature is a real safety design and test concern, but standards, operating modes, installation, measurement conditions, and jurisdictions matter. A pane count cannot certify a surface, and this illustrative model cannot predict one. There is still direct evidence for the basic direction. In one peer-reviewed domestic oven experiment, changing the studied door from double to triple glazing lowered the exterior glass temperature and reduced energy use in that test. Useful evidence, but one appliance and one setup, not a universal percentage. So why does an oven door use multiple layers of glass? Because the door must remain transparent while making heat cross a sequence of controllable stages. Panes create boundaries. Gaps change gas transfer. Selected surfaces can reduce radiation. Some assemblies move cooling air. Frames, seals, and edges complete the path. The panes look redundant only because most of their jobs are invisible. That also explains what the layer count cannot tell you. It cannot identify the coating, prove a sealed gap, reveal a fan route, predict the outer temperature, or establish that one door is safer than another. To know a particular oven, you need its exact documentation and its complete, intact assembly, not a guess from the window. Next, leave the kitchen for another system that looks wrong from the outside. Why can a package travel away from you before coming back? The route may look backward until you examine the network behind it.